Hello, welcome again as we look at Thomas Engel's and Philip Reid's physical chemistry textbook homework problems. Uh, in this video, we'll be looking at chapter 2, which has to do with like expansions, work, heat, and all that jazz. It's actually heat, work, internal energy, enthalpy, the first law of thermodynamics. It's a lot of things, but it mostly is setting up a lot of the systems that we'll be using going forward. We'll need a lot of our ideal gas stuff, but we'll be learning a lot of new stuff as well. So let's start things off. The problems we'll be looking at are problem 3, 5, 12, 21, 24, 25, 31, and 37. So starting right off with problem number 3. 3 reads a 2.50 mole sample of an ideal gas for which the heat capacity at a constant volume, the molar heat capacity at a constant volume is 3 halves R, is subject to 2 successive changes in state. 1, going from 25 degrees Celsius and 125 times 10 to the third pascals. The gas is expanded from isothermally against a constant pressure of 15.2 times 10 to the third pascals to twice the initial volume. The second one is at the end of the previous process, the gas is then cooled at a constant volume from 25 degrees to Celsius to negative 29 degrees Celsius. And then they want us to calculate Q, W, delta U, and delta H for each of these stages. So our heat, our work, our internal change in internal energy, and change in enthalpy for each stage. Also calculate Q, W, delta U, and delta H for the complete process. So we'll start by writing down what we know right off the bat. The only thing we're given that is going to be constant throughout is N is 2.5 moles and C sub Vm is 3 over 2 R. R is going to be our ideal gas constant in joules per mole Kelvin, so 8.314. Now we need to determine for step 1, for situation 1, situation 2, and situation 3, the state variables for this ideal gas, which means we need to find our T, our P, and our V. Some are given, some are not. So for situation 1, our initial starting place, they say T is 25 degrees C. We need to always be converting. All A, B, K, well, A, B, C, always be converting. So plus 273.15 goes to 298.15 Kelvin. And they give us a pressure of 125, so essentially 125,000 pascals. Now we may want to go ahead and put that into a more useful unit, such as bars, but we can leave it there. We can leave it there for now. And we want to know what is our V1. That's only one missing. And situation 2, we said it was isothermal. So 298.15. We say a constant external pressure, so of 15.2, so 15200 pascals. That's the P external. And our volume, our V2, is equal to 2 times V1. And of course, our T3, our situation 3, we don't have much here. We just have that T3 is negative 29 Celsius. And so that plus 273 puts us at 244.15. And let's see, do they have a V3? Let's see, our volume. Okay. At the end of the previous, cooled at a constant volume. So whatever our V3 is, it's equal to our V2. And so that means, and we don't know our P3. Okay. So the first thing we want to do is calculate our volume. How do we calculate our volume for the initial step? Because we'll need that before we go any further. And that's going to be V equals nRT over P. So nRT over P. What is that? So we have to take into account what is our pressure. We have to take into account what is our volume. So let's see how many pascals in a bar. How many pascals in a bar? Let's think about that real quick. I do believe there is 10 to the 5th pascals in a bar. So we have in the first situation 125,000. We're going to divide that by 10 to the 5th. So that means our pressure is 1.25 bar. So we have, let's see, 2.5 times 0.08314 times 298.15 over 1.25. So 2.5 times 0.08314, 298.15 over 1.25. Do that, you have a volume of 49.5, we'll say 58. Technically, we should round it 49.6, but we'll keep another sig fig right now. That's liters. Now, while we technically don't know what is the internal pressure P2, we do not need that. But we do need the volume. The volume, as we said, is double for this first situation. So double that puts us at 99.15. Technically, from the rounding there, that should be 1.6, but I'm leaving my full number. 1.516, it won't matter too much. Now, as I said, 99.16, this is the same. So we need to find out what is our P3. P3 is just going to be equal nRT over V. So just doing the same steps. 2.5 times our 8314 times 244.15 divided by 99.15 or 16. And then we can multiply by 10 to the 5th just to put it in the same units. And we got what? Something like 51 point, what is it? 51.18 times 10 to the 3rd pascals. We'll just leave it in pascals. Okay, so there is our super useful numbers. So we got to remember these as we move forward. Now we have those. We need to think about how do we determine Q? How do we determine U? How do we determine W? Always U is Q plus W. But you could also find U another way. Delta H can be found two different ways. It could either be the Q at a constant P, or it could be delta U plus delta PV. Now, our work is always negative P external delta V, and our heat is always our C sub whatever delta T. Now, the last thing we need before we finish up is our C. Right? We got a C sub V, but we need a C sub P, just so we can do it at all situations. So the helpful thing you need to memorize, C sub P sub M minus C sub V sub M equals NR. What? Equals just what? R, essentially, since it's C sub P. So that means we'll just X minus 3 over 2R equals R. So what is C sub P sub M? That's 5 halves R, because 5 halves minus 3 halves equals 2 halves, or 1. So C sub P sub M is equal to 5 over 2 times R. Now, we can calculate for each of these steps. In the first situation, we are doing a isothermal expansion. Isothermal expansions means we can do work equals the external pressure of negative 15.2 times 10 to the third pascals times our volume, which is 99.15 minus 49.58, and a Pascal liter, and then we have to turn liters into meters cubed. A Pascal meter cubed would be a joule. So meters cubed over 1,000 meters is equal to the number of joules. So our 99.15 minus 49.58, that's 49.57. Multiply that by our pascals, 15.2 times 10 to the third, and add a negative sign. And then we divide by 1,000 to get this into joules. So our work from going from situation 1 to situation 2 is simply 753.5 joules. Now, for our isothermal expansion, our heat is equal to the opposite of our work. So the heat for an isothermal expansion is going to be equal to positive 753.6 joules, or 753.5 joules. Now that makes U equal to 0, because U plus negative 753.5 plus positive 753.5 is going to be equal to 0. But another way to calculate delta U is equal to C sub V, which is 3 halves R, times delta T. Isothermal expansion, our delta T is 0. So work is, the internal energy change is 0. Also, delta H is going to be 5 halves R delta T, also 0. Isothermal has no internal energy change and no enthalpy change. So we've calculated our Q, our W, and our W, our internal energy, and our heat for those steps. Now to do from 2 to 3. 2 to 3, we have a situation where we have no change in volume. So the work from 2 to 3 is going to be whatever the external pressure is, doesn't really matter. Delta V, which we're going from 99.5, what did I say? 99.16 to 99.16. By very definition, it's going to be zero. Zero work done under a isochoric, a constant volume situation. Now heat, a little bit easier. Heat is going to be Q equals constant volume. So we want 3 halves R times delta T. So 3 halves times 8.314, which is our R, times we're going from, let's see, final minus initial, so 244.15 from 298.15. So we're releasing heat. We do that, and we should get 3 over 2 times 8.3 times. That's it. Okay. Yeah. We get negative 673.434, and that's joules per mole. And we have to take into account we have 2.5 moles, and this gets us into joules. So negative 1683 joules, because the units of that is joules per mole Kelvin. So Q should technically be, Q is N C sub Vm delta T. We're just taking that into account later. But okay, so there's our joules. Now, due to the handy-dandy definition, delta U is heat plus work, or it's also Q sub Vm delta T. So our delta U is just going to be negative 1683 joules, but our delta H is going to be N C sub Pm delta T. So instead of 1683, we have to exchange out 5 halves. So times 5 divided by 3. It changes our number to negative 2806 joules. 2806 joules. So it's a significant change. A little bit more for enthalpy, a little bit less for internal energy. Finally, for this total process, we add our delta H. Delta H is just this because it's delta H plus U. So delta H is going to be negative 2805 over 2806 plus 0 is 2806. Delta U is going to be negative 1683 plus 0, just that. Our Q is going to be our what? We have negative positive 753.5 plus our negative 1683. So that gives us what? negative 929.4, 924, 9.5, 29.5. And our work is just going to be our negative 753.5 plus 0. Negative 753. Now, these numbers don't really mean a whole lot to us right now because this is not a cyclic cycle. Had we taken one last step and closed up the cycle, we might be looking at a little bit cleaner numbers, where you would find out the delta U ends up being 0 and the delta H ends up being 0 for the whole thing, while the heat and the work are not. But this is just the process of which we will use as we work through here. We find the various values at various stopping points. We solve for heat or work. We use the various different definitions to make this easier as we go. Okay, so with problem number 5, it's a completely different beast. I have Count Rumford has observed that using a cannonball in machinery, a single horse could heat 11.6 kilograms of ice water of temperature 273 Kelvin to 355 Kelvin in 2.5 hours. Assuming the same rate of work, how high could a horse raise 225 kilograms weight in 2.5 minutes? Assume the heat capacity of water is 4.18 joules per gram Kelvin. So the first thing we need to do is write down all the values we have. We have 273 Kelvin. We have 355 Kelvin. Those are our initial and final temperatures. We have the mass of water as being 11.6 kilograms. And the heat capacity of water is 4.18 joules per gram. 4.18. We don't actually need the 4. The 4 should be there, but 4.18 joules per gram Kelvin. And this is over a time period of 2.5 hours. What we're going to solve for is we're calculating that the heat produced by the horse in 2.5 hours will be similar to the energy produced, the work done by the horse in 2.5 minutes. If we can find the rate of energy flow for the first situation, we can use that rate of energy flow for the second situation and find out how much work. So I've already written down a couple of these things. That heat is mass times heat capacity times delta T. Since the mass is 11.6 kilograms and the heat capacity is joules per gram, we're going to say 11,600 grams times 4.18 joules times our temperature, their delta T, which goes from 355 Kelvin from 273 Kelvin. That will give us energy in joules. We may want to convert this into kilojoules, as it will be a very big number. 0.18 times 355 minus 273. That is 3,976,016 joules. So I'm going to convert that into 3976 kilojoules. And we're going to run this into kilojoules per hour. So that's produced in 2.5 hours, meaning the horse produces approximately change in energy of 1,590 kilojoules per hour. Now, with that in mind, we need to figure out how much of that is it per minute, because we do this in 2.5 minutes. So in that matter, in 1 hour, there is 60 minutes. So the horse produces approximately 26.5 kilojoules per minute. Now, applied over 2.5 minutes, the horse could do approximately 66.3 okay, let's write this over. 66.3 kilojoules. Now, to calculate the work, we need to find out the work function, among other things, is a force applied over a distance. And we're trying to find that distance. So, and a force is a mass times acceleration. So equals our 66.3 kilojoules. Force times distance. And a force is a mass times acceleration. So mass times acceleration times distance is equal to we'll say 267 joules. I'm unrounding from my calculator. The mass of that object is, what did we say? It was, we're lifting a cannon, which was, oh, and the cannon was 225 kilograms. 225 kilograms. And the acceleration, of course, would have to be gravity, 9.8 meters per second squared. And a force is a kilogram meter per second squared. So times our D. 66267. With that in mind, we divide out. And so we say 220 divided by 225. We divide by 9.8. And we would be able to successfully lift this 30 meters. Should be able to successfully lift this 30 meters. Yep. Okay, so with that in mind, the distance is lift it 30 meters in 2.5 minutes. Moving right along to number 12. Number 12 says, in a reversible adiabatic expansion of 1.75 moles of an ideal gas from the initial temperature of 27 degrees Celsius, the work done on the surroundings is 1,300 joules. If C sub V sub M, so molar heat capacity at a constant volume is 3 halves R, calculate the heat work, internal energy, and change in enthalpy for for this system. So adiabatic reversible expansion. So step 1. Write down what we know. Our N, unless we choose to accept it, is 1.75 moles. Sorry. Our T1 is 300 Kelvin. Our work is negative 1,300 joules. And our C sub V sub M is 3 over 2R. Now, because of this, we also know our C sub P sub M. Remember, C sub P sub M minus C sub V sub M is equal to R. So if C sub P minus C sub V is R, and we started with R, then 5 halves minus 3 halves equals 1. So C sub P sub M is given by the fact that we know C sub V. So we have all our constants. So heat work. Now, remember our handy little tools. If we know U is equal to Q, delta U is equal to Q plus W, but it's also equal to Q sub V sub M. Delta H is equal to, so we don't, normally we would say, oh, it's a reversible adiabatic expansion. We might need our weird PI, VI, gamma over gamma to the gamma equals PF, VF over gamma. But we have actually all we need. We're given work. You got to remember that for a reversible adiabatic expansion, Q adiabatic is actually 0. That does not mean Q sub V is 0. It means Q for this situation, Q sub V sub M is a specific expansion at a constant volume. That's how we can say delta U is equal to Q is equal to just W because of because of that. So delta U is equal to negative 1300 joules, but this is also equal to Q sub V sub M. So that's a really neat thing. If I know C sub V sub M, I say Q sub V is equal to N C sub V sub M delta T. Wow. Because of that, we can find out what is our change in temperature. What is our change in temperature? So we can set negative 1300 equals to 1.75 moles times 3 over 2 times 8.314 joules per mole Kelvin times delta T. From there, we can figure out what is our change in temperature. 1300 divided by 1.75 times 2 over 3 divided by 8.314. So, our change in temperature is negative 59. Let's say 57. Okay. That's our delta T. So if our T initial, so if it's TF minus TI, we add that to 300. So, and we have our T2 is negative 240. We may not even need that. Well, we only really need this number because delta H, if you remember, is equal to N C sub P sub M delta T because it's Q sub P. So it's just going to be 1.75 times 5 over 2R times our negative 59.57. We already got a U. We already got a W. Our heat is 0. So 1.75 times 5 over 2 times 8.314 times negative 59.57. So the enthalpy change is negative 2166 or 2167 joules. That's actually relatively easy, all things considered, compared to all the other possible problems you could have been asked. What you need to be able to recognize, though, as you work through these problems, is that sometimes, not always, we have multiple different ways of looking at the same thing. Said the heat under adiabatic expansion is not the same as the heat at a constant pressure, but know that enthalpy could be defined as all those things of delta U plus PV, but it could also be Q sub P. So you always use the easiest function, always. Welcome to number 21, our first real calculus problem. The heat capacity of solid lead oxide is given by C sub P sub M equals 44.35 plus 1.47 times 10 to the negative third, temperature over kelvins in units of joules per mole Kelvin. So this really strange C sub P must be integrated over this temperature. Calculate the enthalpy of 1.75 moles of lead oxide if it is cooled from 825 Kelvin to 375 Kelvin at a constant pressure. So let's look at this. So Q is going to be equal to the integral of N C sub P delta T. What is C sub P dt? But D is the delta T is actually just the integration of that. So writing that 1.75 moles integrating from 825 to 375. Now this part isn't really that hard. We just got to remember our rules of integration. Normally, that's a dt, and the other one is 1 plus 1.47 times 10 to the negative third T dt. That over Kelvin is so that your units work out. So if you integrate this over Kelvin, you integrate that temperature, joules per mole Kelvin, you don't have Kelvin squared. These guys have to add into each other. So you integrate this guy, integration of dt is just going to be, so carry this over, so times, so that's just going to be 44.35 times our 375 minus 825. But this next part is a little bit harder. Since it's T dt, when you integrate x dx and you integrate that, that's going to go to x squared over 2. So what we have now is I'm going to add the second part, the next line, 1.47 times 10 to the negative third over 2. And that's where we're going to get t squared, 375 squared minus 825 squared. That if that's Kelvin, you would have Kelvin squared minus Kelvin squared. So to keep this all right, you need that over Kelvin. So step one, let's evaluate the various parts of this. You could do this all in one step, but we're going to take our time. So 44.35 times 3, the difference between 375 and 825, that's, so write this down, 1.7. Oh, I might out of room. I took up too much room. Fun. 1.75 times negative 19957.5 joules per mole Kelvin plus, so the next part on back, 1.47 times 10 root negative 3 divided by 2 times the difference between 375 squared minus 825 squared. So it's going to be a big, the 10 to the negative third, which would normally make that a really small number, make this a very reasonable addition. So the second part is negative 396.9 joules per mole Kelvin. It's not Kelvin Kelvin or unitless because of that setup. So add that little modification onto the previous modification. So minus 19957.5. So you have negative 20354.4 times 1.75, and you get your heat is negative 35620.2, or you can say negative 35 kilojoules. Joules per Kelvin. We already calculated the Kelvin when we multiplied by the temperature. So it's just joules. And that is all it is to it. This is not a hard one, but it's our first introduction to the usage of calculus to try to calculate a heat capacity. Okay. Had we not had that second part, 44.35 times what? 1995 1.75. You would have got, it's not, you'll never really make a huge major difference, but in these types of chemistry, you're trying to get as accurate as possible. So had you not had the second part in there, it would have only been 34.9 kilojoules instead of 35.6 kilojoules. But, it's over bigger temperature ranges, bigger and bigger changes. We are trying to accurately show reality, and that's what we're doing. Sometimes at our own suffering. That's what it is. It's PChem. Okay, looking at number 24. Number 24 reads, a 3.50 mole sample of nitrogen in a state defined by T initial is 250 Kelvin, V initial is 3.25 liters. There goes an isothermal reversible expansion until the volume final is 35.5. Calculate work assuming that A, that the gas is described by ideal gas law, and B, that the gas is described by van der Waals equation of state. What is the percent error in using the ideal gas law instead of using the van der Waals equation of state? The van der Waals parameters of N2 are listed on table 7.4. So looking at that, let's write down what all we know. We know a few things. It's a reversible isothermal. So we're only looking at work. Work being defined as, under a reversible isothermal, work is defined as negative nRT ln VF over VI. So let's write that. Our temperature is 250 Kelvin. Our VI is 3.25 liters. Our VF is 35.5 liters. So, and our moles is 3.50 moles. So the work for ideal gas, that's actually rather easy. Negative 3.5 times 8.314 joules per mole Kelvin times 250 Kelvin times natural log of 35.5 over 3.25. Liters over liters cancel out. With that in mind, we'll get units of joules. 3.5. 0.314 times 250 times the natural log of 35.5 over 3.25. Turning the, that gives us joules of negative 17,393. Now, with that in mind, okay, so I looked up our values from the back of the book. Our A was 1.37 liters squared bars per mole squared. Our B was 0.0387 liters per mole. Now, what we have to do to calculate our work is take the integral of our work. Our work is P delta V. I kind of screwed up and did the work in advance because of the screw up here. But so the integral of negative P delta V. Now, since we don't know pressure, we have to exchange pressure for our van der Waals equation of state. So negative, that'd be nRT over Vn, V minus Nb, minus n squared A over V squared. Now, because that negative, it carries it through. So that makes negative nRT and positive n squared A over V squared. So take the integral of that. You have to integration by parts. So you integrate V minus Nb. So that becomes 1 over V, essentially the ln Vf over Vi. Because it's V minus Nb, it becomes negative RT and RT ln Vf minus Nb over Vi minus Nb. And the n squared A over V squared becomes essentially 1 over x squared becomes negative 1 over x. So you gets positive n squared A over times negative 1 over Vf plus 1 over Vi. So that negative carry through. Then it's just a matter of doing that. So rewriting up there, plug it in. So 3.5, 8.314, 250 Kelvin, natural log 355 minus 3.5 times 0.0387 all over 3.25 minus 3.5 over 0.0387. So calculating our new value of Vf over Vi, got natural log of 11.3546. Doing all those steps, you get negative 17674.9 joules. But we have to consider the second part up here. So we got negative our A, we got our n squared, 3.5 squared, and so 1 over 35.5 minus 1 over 3.25 liters. So this is going to be in bars, bar liters. So we have to turn bar liters into joules. So turning a bar into pascals is 10 to the 5th, but meters cubed over liters, that's 1,000. So essentially, and a joule is equal to a Pascal meter cubed. But essentially, 1 bar, 100 bar liters is equal to 1 joule. No, sorry. 1 bar liter is equal to 100 joules. So you multiply by essentially 100 because 10 to the 5th divided by 10 to the 3rd is 10 to the 2nd. So you do that step, it becomes positive 469.1 joules. Add those two terms together, you see your total energy for the van der Waals is negative 17,205. But what we have to do here is then calculate the error. The error is actual, the difference between the actual and your inaccurate one, all divided by your actual. So the difference divided by your actual times 100. So 17,393 we got from the first one. 17,205.8 we got from the second one. Take the difference of that divided by 17205.8 times 100 gives us 1.09% error. Not perfect, but it's pretty close. That's why most times we teach this. We don't bother to go into being super accurate like that. But as I said, this is PChem. We're nitpicking. That's what we do. So that's that problem. Three more to go. Number 25. A major league pitcher throws a baseball with a speed of 162 kilometers per hour. The baseball weighs 235 grams. Heat capacity is 1.7 joules per gram Kelvin. Calculate the temperature rise of the ball when it's stopped by the catcher's mitt. Assume no heat is transferred to the catcher's mitt and the catcher's arm does not recoil. He or she catches the ball. So assume that the kinetic energy of the ball is completely converted into thermal energy. So it's a cool problem. Not really that practical because it's like, oh, this ball rolls down a frictionless plane and yeah, not actually happening. But it works for our all intents and purposes. Let's write down what we have. So we're doing a kinetic energy problem. So we have what? So the velocity is 162 km per HR. We have a mass of 235 grams, and we have a heat capacity of 1.7 joules per gram Kelvin. So kinetic energy is equal to 1/2 mass times what? Velocity squared. Yeah, that sounds about right. And that's going to be, keep in mind, a joule is a kilogram per meter squared per second squared. So we need 235 into kilograms. So that part's easy enough. 1/2 times 0.235 kilograms times, we have to turn this into, well, like kilometers per second. So 160, let's do that quick convert. Kilometers per hour. So there is what? In 1 kilometer, 1,000 meters. In 1 hour, there's 60 times 60, so 36,000 seconds. So 162 times 1,000 divided by 3600 equals 45 meters per second. Pretty good. 45 meters per second. All that's squared. So 45 squared times 0.235 divided by 2 means how much energy does the pitcher pitch? It's what? 237.9 joules. Now, assuming all that is converted, this is going to also equal the heat. So heat, as we know, is C sub P was CMC delta T. C delta T. So with that in mind, we give the heat capacity in grams, so it's going to be, that's equal to what? 235 grams. Heat capacity is 1.7 joules per gram Kelvin, and we're just solving for our delta T. So this one's actually not that hard compared to the last couple ones we just did. 237.9 divided by 235 divided by 1.7 means the ball only heats up about 0.596 Kelvin. Not very much. And of course, calculating for recoil and all that, the heat loss, it's going to be a little bit less. But the ball will heat up a fraction. So it happens. "31 is another kind of silly one. Suppose an adult is encased in a thermally insulating barrier so that all heat evolved by metabolism or foodstuffs is retained by the body. What is her temperature increase after 2.5 hours? Assume that heat capacity is 4.18 joules per gram Kelvin. Heat produced by metabolism is 9.4 kilojoules per kilogram per hour." So this one is just really a conversion problem. So we have to, let's write down the 3 things we know. We're trying to calculate for 2.5 hours. That's our T. Our heat capacity. Heat capacity is C is 4.18 joules per gram Kelvin. And our heat, essentially our energy, is equal to 9.4 kilojoules per kilogram per hour. So, okay. So really the only thing you need to worry about is almost nothing. You just have to reason through this one. A kilojoule per kilogram is the same as a gram per joule per gram. This is approximately equal to a 9.4 joule per gram hour, because you have to multiply kilojoules by 1,000 to get it to joules, but you have to divide this by 1,000 to get from kilograms to grams. So we do 9.4 times 2.5 hours. And that would calculate how much energy is produced by the metabolism based on the person's body weight. So 9.4 times 2.5 is simply 23.5. 23.5 joules per gram. Now, if we're talking about the heat capacity here, then we are going to divide by 4.18 joules per gram Kelvin. Gram cancels gram, joules cancels joules, and you would get, what is their temperature change? A simple value, 4.18. You would calculate that temperature change would be 5.6. We'll say 5.62 degrees Kelvin. Now, if they want to go one step further, your body temp is 37 degrees. So, heat of all, what is her temperature increase is 5.62. But if you want to go body temp, 37 degrees, which is 310 Kelvin. You go 310 Kelvin, so plus our 5.622, it becomes 315 point, what, like, it's a 310.15, it'd be 0.7. So that's our new body temperature after this silly problem. Last one, number 37. Calculate the change in enthalpy and change of internal energy of the transformation of 2.5 moles of an ideal gas from 19 degrees Celsius in 1 atmosphere to 550 degrees Celsius in 19.5 atmospheres if the C sub P sub M is 20.9 plus 0.042 T over K in units of joules per Kelvin mole. This one's a little bit harder and a little bit of knowledge, and we'll work our way through this one. But the last one, let's write down what all we have. We have our T1, which is 19 degrees, which is 1 plus 273.15 becomes 292.15 Kelvin. Our T2 is what? What did we say? What did it say? It's 550. 50 plus 273.15 becomes 7, 8, 23 Kelvin. Our P1 is let's see, P1 is 1 atmosphere. And our P2 is 19.5 atmospheres. And our C sub P sub M is 20.9 plus 0.042. Now, P delta V. Now, I don't think I actually use, well, let's see. I'm trying to decide whether I actually need this. You get a slightly different number depending on how you do it, but you could probably make your life a lot easier just by, well, just by doing it the simpler way. Because technically this is an adiabatic exchange where everything changes. You could calculate this and figure this out, or you could I guess it's not a reversible adiabatic, but it is an adiabatic exchange. But so the easiest one to do is just calculate your delta H. Delta H is, and the last thing we need to know is the moles is what, 2.5. 2.5. So easiest thing to calculate is delta H. 2.5, and then we're going to integrate 20.9 plus 0.042 T. Well, that's dt. So let's do that. So 2.5 times 20.9 times our 8, getting all backwards, 823 minus 292.2. Plus our 2.5 times 0.042 over 2, 823 squared minus 292.2 squared. 2.5 times 20.9. Do the first part, figure it out, and then do the second part, figure it out. All right, so that's the first part is 27734. Second part, 2.5 times 0.042 divided by 2. 823 squared minus 292. So, and that's plus 31077. So we're kind of in a conundrum. The easiest thing to do is delta U equals N C sub V sub M delta T, but we're not given N. Well, we're given N, but we're not given C sub V M. And we do know C sub P minus C sub V equals R. So we can actually, even though our C sub P is some really weird equation, we can simplify this and just say C sub P minus R is equal to C sub V. So we can say that N, the integral of, instead of 20.9, it's now 20.9 minus 8.314 plus our 0.042 T over K. All that dt. So 20.9 just becomes, instead of that, 9 becomes 12 point, we'll just say 586. So it becomes 2.5 times 12.56 times the difference between 823 and 292.2. So times 820, 292.2. That one goes to 83909. The other part are 2.5 times 0.042 over 2. 823 squared minus 292.2 squared. So 2.5 times 0.042. That part doesn't change. The part actually doesn't change at all. 31077 plus 31077. You can add that. So that becomes 83909 plus 31077. Add those up. Our new energy. What did I do? Oh, I fucked up. 83909 plus 3. So, what did I screw up? Screwed something up. Oh, I see why I screwed up. I screwed up in this calculation right there. That is 16,693. Oh, 694, we'll say that. Plus 310.77 gives us 47771. That's the, if we round it to the proper decimal place, 47.8 kilojoules. Okay. Now let's do it the hard way, the annoying way, which is, okay, we need the volumes initial and volumes final to do it adiabatic, because delta U is equal to delta H minus PV, or delta PV. So, and under these circumstances, our PV has to be what, like our PF VF minus PI VI, and then turned into joules. Well, we're given the pressure and we're given the temperature, so we can find out what is our volume. I'm going to skip a little step writing it out, but because it's PV equals nRT. So our volume initial, 2.5 times 0.08206, because it's atmospheres, 1 atmosphere, and 292.2. So our VI is what, like 59.94. Our VF, similar conditions, 2.5 times R times, in this case, it's 823 divided by 19.5. Our VF is 8.66. So 8.66 times 19.5 minus 89.94 times 1. So our PF minus V, this whole term, simplifies to 78.93 atmosphere liters. And the conversion rate is what, like 101.325 Pascal atmosphere liters to joules. So times 101.325. 101.325 means the PV is 799, we'll say 8. So take our delta H. Our delta H from the last problem, from the last step, was 58811. So 58811, subtract our 7998. And what are we going to get? 811 7998 gets us pretty close. 50 point. Oh shoot, that's I screwed up my math. 8.66 times our 19.5 minus, that's 59.94. That's actually 108.93. 108.93 times 101.325 gives us 11,037. 11,037. So 58,811 minus 11,037 gives you 4,774, which rounds to what, 47.8 kilojoules. You get the same answer. You get the exact same answer. You do it the easy way because you already kind of worked it out, or you do it the hard way, you're going to get the same answer. That's the nature of a state function. And that is the end. That's where we're going to leave it. Thank you for your attention. Hopefully this helps answer some of these difficult questions. See you for video 3 later.